This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, so we can officially start. Before we begin, as I was saying, no reports for this workshop, but it gives you an opportunity to set up your environment and, as I said, to play with Python a little bit, brush up your Python skills. And the first workshop material, I have already posted it. This is workshop 0, if we start to count from 0, right? The next workshop on optimization starts next week. That will be a 2-week workshop. So that will go on from week 2 to week 3. And then the report will be the week after, the week after that. And there will be a report associated with that one. And then it will give you a chance to practice your optimization knowledge, theoretical knowledge that we do here. And I'm also very much on top of the recording problem saga. And you know, the IT has some idea what is happening. So that means hopefully there will be a solution next week. So it's a funny story. I want to first figure out what's going on. If the story is what they told me, it's a really funny one. I'll tell you later. Okay. Any questions? Any concerns? Anything? Nope. Then we continue with the cutting plane methods for convex optimization. Actually, I will ask you at the end of this unconstrained slide set whether it was a good idea or not putting cutting plane methods first before the gradient methods. So I will do a kind of a quick survey in the classroom. It seemed like a good idea to me because it ties up to this number guessing game we all played when we were a child. And the idea there is to decrease the volume of the search space, right? And in the bisection case, you just halve it. By the way, I uploaded a newer version of these slide sets. So you should take the authoritative slide set is what you see after the week is over. So what I post earlier is not the latest version usually. I always do some last-minute improvements to the slides. And I mentioned the center of gravity method, and I'll come back to this, but I would like to first solve this question 4 about the Voronoi description of half spaces, because it kind of allows us to play with some geometry. Some of the questions I solve are like that, so it gives you some skills that are relevant to the material. Let's do this one. I think it's really instructive and kind of useful. So we have the question, and you can see it there as well. And then the Voronoi diagram is as I said, the nearest neighbor. If you do a nearest neighbor clustering algorithm to the cluster centers, which are these dots, then that's what you get, you know, under Euclidean distance. When you say neighbor, what do you mean by neighbor, right? In terms of what distance? You need to define a distance metric. We will come to that when we discuss clustering, unsupervised learning. A and B, the problem has nothing to do with, kind of has to do with this diagram. A and B are distinct points in Rn, show that the set of all points that are closer in Euclidean sense to A than B which can be described as such, is a half space, right? So we have a let me get another color, right? So, or here, A, and then we have B, right? And then all the points that are closer to A than B, as you can imagine, if I draw a line that is orthogonal to the AB connecting line, then everything to the left of that will be closer to A than B, right? So that's by definition a half space. So this is the half space that the question is talking about. And that half space, like everything else, can be defined as a set in mathematics, right? So there is the famous saying, the one mathematician said, I don't know who said it, but he said, nobody can, kick us out of the paradise that Cantor has created for us. And Cantor has developed the set theory in mathematics. So most of the modern mathematics is built upon set theory. So the set is then X element of maybe Rn, right? Is it, to be more precise, such that no. What happened? Anyway, this semester is funny. Anyway, such that, right? This means such that the norm, Euclidean norm, x minus a is less than or equal to x minus b. So distance to a in the Euclidean sense should be less than or equal to than the b. So that's the set. That's the half space H. And let me call this H. Maybe with the color coding. So that's the half space H. Half of the space. You divide. This line goes to infinity. Right? So this line goes all the way to infinity. Because any point towards the infinity can be also between A and B. All right, so actually it's pretty quick. Let's do that. We can write this. First, we can use the fact that describe it explicitly as an inequality of the form C transpose X less than or equal to D. Sorry, not BD. So, and C and D parameters, right? What is C and D? That's the question. So this is a definition of a half plane. You all know that? Some of you know that? Some of you don't know it. So I get a lot of different hand shaking. So we go to some notes. So let's define a half space. In 2 dimensions, it will be a line that divides it, right? So if I divide, if I put a line, right? And then I put a orthogonal vector to the line. Let's say this is A, right? And then this is X, all right? And then I take any point on this line Y. And if I write the vector Y minus X, it can be also Y can be on the other side too, right? So what would be the dot product of these two? Because they're orthogonal, it will be 0, right? So we have then A y minus x equals 0. So that would be any y, let's call this x0, any y on the line will have this, okay? And then actually, you can also write it this way, A dot, this is dot product. Dot product is A transpose vector, and then y minus x0 will be then the row column vector, and then A is the transpose, then becomes a row vector. You do a dot product. So you can also write this A transpose y equals A transpose x0, and then you can call this as a B, right? So that then determines all the y's will be then on this line. So now move this to an n-dimensional space. It's already in the n-dimensional space. For example, in the 3 dimensions, it will be then a whole plane. The plane will have a normal vector going out. I think my connector is bulking for some reason. Okay, let's try again. So then any point y, and this will be then the x0, and that will be the vector, right? You see what's going on? Then that will be the same formula. Any point on the plane for 3 dimensions will have this property. And then if you make it, then the other question is, then that defines the hyperplane. You know, in 2 dimensions it will be a line. In 3 dimensions it will be a plane. In 4 dimensions it will be a 3-dimensional thingy. So after a point you cannot visualize it anymore. But the formula is still the same. So the question is, how do I then define the half spaces? So it will be then, right? So it will be then y, this vector, any point with respect to this point, x0, that any arbitrary point, and then you have the normal vector. So if you want to define this side, what would it be? It will be then y minus x0, and then dot product A should be greater than or equal to 0. Because the dot product means A dot B is A, B cosine theta, right? And then any point here, for example, then will be then the theta, right? The cosine theta less than 0, greater than 0 means I'm in the same direction. But if it is the other side, let's say the blue side, and then y is here, then it will be then y minus x0a will be less than or equal to 0, because then the theta will be greater than 90 and cosine will be negative. Right? So that's the whole idea. That's how you define a half space. Yeah, we will need this because we want to separate things into classifiers, right? So the dogs versus cats, there will be a boundary. And if your boundary is a linear boundary, then you have a hyperplane. So that's also, or in the clustering, like the problem is asking. I assume this is your background knowledge. So you should have paid attention in your math classes. You see, it's useful. So can we write this then as a half plane? Obviously, yes. So then we need to come up with the C that gives us this normal vector, and then the D that gives us the right-hand side. Actually, if you just write it down from the formula, we can directly derive it. X minus A second norm, Euclidean norm, x minus b, Euclidean norm. If you take the squares, this is also valid because they are positive, right? The norms are positive. So square will be also less than or equal to. So, and then square means then x minus a transpose x minus a. These are all vectors, right? Then less than or equal to x minus b transpose x minus b, right? So we can write it also if you want I xi minus ai square, right? That's what you're going to get, less than or equal to I xi minus bi square. Element by element. That's the vector notation. So then we can write this, open it up, not this one, so let me put this into a parenthesis. So we can write this as this x transpose x, and then minus ax, minus x transpose a, and then another minus a transpose x. So we have then the minus 2 a transpose x, both are the dot products, plus a transpose a here, and a similar expression for this one, x transpose x minus 2b transpose x plus b transpose b. Right, and then we can actually then put the x transpose x's cancel out, first of all. Then I can put the b to this side, so I can have then 2b minus a transpose x less than or equal to, and then b transpose b minus a transpose a. But then I have achieved my goal. We wanted a half-plane description of this format, right? So this was the question. Oops, that's a bad idea. We wanted this question mark. So we end up with then this will be my C transpose, and then this will be my D. Does this make sense? Yes. The normal vector that multiplies x dot product is b minus a. So essentially, as you can expect, the normal vector is some scaled version of b minus a. So therefore, the product of x with that should be less than or equal to d, or you can actually write it the other way. So the less than or equal to version will be this side, and greater than or equal to will be the other half plane. Because this dot product is then coming minus that will be less than or equal to 0, not greater than or equal to 0. Because the x's are in this side. Yep. So that's essentially it. So we have played, sorry about that. Yeah, I should have done this way. So we have played with it and talked about the half planes. Now, this half plane idea, I'm going to use it to talk, just do a recap of the this whole cutting plane method. So if I go to my notes, just to recap this whole cutting plane business, is this. So let's say an example cutting plane method. Right? This is not the best method, but let's say the center of gravity method. So let's say we know there is a solution, x star. We want to find it. We don't know where it is, but let's say we find, I'm just making a very simple version, right? Let's say we put a very big bounding box around it, right? So we know it's between x min, x max, and y min, y max, let's say. But we don't know where inside it is. So and then we choose a starting point, right? So if you this is actually pretty bad. It's close to center, so let's choose it here. So remember the number guessing game? The counterpart is the center of gravity method in higher dimensions. So what is the center of gravity of this whole thing? Is this one. So it would be then x0, right? And what do I do at that x0? I look at the gradient. And if it is a minimum, so if I try to do a mean fx, x, and then x star is then arc mean x fx, right? That's the solution, which I don't know. The gradient then will be in this direction at this point, right? Somehow, let's assume a convex function, f convex. So if that is the case, then all I need to do is create a cutting plane corresponding to this, and eliminating this side and keeping eliminating this side. Yeah, so I eliminated this side, so the other side is still in the game. So then I find again the center of gravity. Let's say this will be x1, and I look at maybe it is a different shaped ball, and maybe it's unimodal or something. Then if this is doing that, then I need to create another half plane perpendicular to the thing, and then eliminate the other side, because I know I want to minimize. I cannot go the other side. It will maximize things, right? And so on. So you can then find the center of gravity of this one, and x2, and maybe the gradient is looking this way, and then you have this. Why is this doing that? Right? And then this gets canceled. So you actually add the constraints, right? Each time add a new constraint. And also, by the way, remove redundant ones. Totally by chance, I made a good example. So now the first constraint is actually now redundant. So this is 1, this is 0, this is 2, this is 1, this is 2. So the 0th constraint is a bit redundant. So because our search space is now this, right? So and so on. So if you continue, you can come to an epsilon neighborhood. That's the whole idea. So it's just the number guessing game in higher dimensions. You decrease your volume. Any question? Is this clear? Is this intuitive to you? Or not? Who says this is so intuitive, I really like it? And who says it's not intuitive at all? Who are the best politicians in the room? who say no comments? Okay, you don't give me anything, so I'm going to do whatever I want then. you need to tell me. Yes?
Vector A is a vector
Yes.
about the place, like, is it being at x0, then it is at x1. Each time x.
A is a vector, just a vector. I mean, you know, it has A1, A2, A3 to AN. It's a vector.
It has a location.
No, it's a vector. Vectors don't have a location.
So how do you use a vector to?
I mean, vectors, I mean, you can put it to the origin, of course, but I mean, A is A, like A is like A1 to AN, right? And I usually use the column vectors. Some books use row vectors.
So how can you use a vector to create a constraint?
Just like this half space. So you use this half space idea. Half space that we have discussed, right? This whole half space idea is used. Yeah, you should brush on your linear algebra. I mean, the machine learning has a lot of linear algebra, let alone the optimization. Right? It's a hard requirement. So, okay. Any other question? Now, actually, there's an easy question, the question 5. Yeah, let's continue with that. So this is telling you, now I do the volume reduction, what's the best case scenario? This is a nice, simple one. Progress in iteration k of a cutting plane algorithm, right? And can be quantified by the decrease in volume of the search space, just like the number game. You half the best case scenario, right? That's volume k plus 1 should be then less than the volume k. Argue that the worst case volume reduction cannot be better than half. So that means even if I do this in higher dimension, the best case scenario is I divide my volume into 2. So that's actually straightforward to show, but I thought, again, it is kind of instructive to show this. And even if I don't do this first in the next year, I'm going to do it in the constraint optimization. So I'm not going to remove the cutting plane methods because I think they are a good chance for you to catch up with your some geometry that I'm going to use also in machine learning a lot. So let's look at that. And I'm going to give the very simple argument. So at the cuts of this form, right, at the in this case, the gradient will be A. So the half spaces, the new constraints A transpose, say, in this case, Z minus XK, right? The kth iteration. And in this case, XK plus 1. Let me write XK plus 1. That's the point. And at that point, you have the A, right? And then that is less than or equal to 0 will be then this side. No, the gradient then needs to be on the other side, right? So the gradient needs to be done this way. A should be this way. Then the shaded area will be the less than or equal to 0 because of the cosine theta, theta being greater than 90 degrees. So each cut brings these half spaces that I'm intersecting with each other. So we can define a function, rho A. So let me do this so that the rho A has this volume ratio. Volume of the set, this initial set Pk, right? And then intersected with the new half space, which is Z, such that A transpose Z minus xk plus 1 less than or equal to 0. So that would be then the volume of this shaded area, essentially. So let's exactly. That will be the volume of that area. It's in 2 dimensions. It's an area, but volume. I mean, volume of that shape, shaded region. Volume of that shaded region. In 2 dimensions, it's area. In 3 dimensions, it's something, and then that region, the volume of that region. So that region's volume divided by volume of the whole thing, which is the volume of pk shape. So the pk shape is this, right? And then all we need to show, and then this is another example. So this is example 1, and this is example 2. If you were here and then gradient directed to the other way, you are minimizing or maximizing. Somehow you do the right thing, and then discard the other option, right? Is the number greater than less than 50, right? And then that will be again a shaded region. So the whole argument is simple. So you actually, what you're doing with this cut is there are 2 options. So you have this pk plus 1, the new shape. Once you discard wait, which one do we discard? So we discard the white one and keep the shaded one. In any case, it comes to the same point. There's an interesting symmetry here. Of course, we need to discard one of them, because one of them is irrelevant. So the next one is either this, based on what you discard. Either you discard the half plane less than or equal to 0, or you discard the complementary set, which is the shape intersection z a transpose z minus xk plus 1, iteration greater than or equal to 0, right? So they basically, obviously, pk is a union of pk plus 1 and pk plus 1, right? Is all clear? So then all we need to know then is, if this is rho A, then actually if you do the same thing with the minus A, right? If I do a minus A, then that already changes the sign of the inequality and tells me this is the other side, this is the other half plane. So therefore, we have rho A and rho minus A. Rho minus A will then handle this pk plus 1 bar with the same definition. Then they need to add up to 1, because then the volumes of these will be, because volume of pk plus 1 plus volume of pk plus 1 bar will be equal to the volume of pk. And because they are in the denominator, they will just add up to 1. Normalize with respect to the volume. And then what does this tell you? This tells you that because we have this ratio relationship, rho A plus rho minus A is 1, the best, just like in the number guessing game and bisection, the best you can do is, maximum over A. Where should I put the A such that I find the best situation? The best case is maximum A rho A will be then greater than or equal to 1/2. So if you're lucky, you may get sometimes lucky, then you discard a huge chunk of the search space. But on the expectation, you discard only half of it, and in the worst case, what's the worst case? Worst case volume reduction can never be smaller than 1/2. So in the worst case reduction cannot be better than 1/2. So that's something you also know from the bisection. So we actually, the whole idea is, again, the regions and the volume, and then this ratio of the volumes of once you intersect the half space, discarded half space, and the search space half space, where the solution is hopefully there, that intersection ratio to the total volume and the complementary is equal to 1. Therefore, you cannot do better than half in the worst case scenario. Sometimes you get lucky, you can do better, but in the worst case, you cannot do better than half. All right, so that kind of ties up to what I have been also showing. Right, you're getting maybe more than half sometimes, but the worst best is half. Are you with me, or is everybody lost? Nobody has done analytical geometry? Well, you actually, this is a good that I put it here. You know, the cutting plane methods are not terribly important from optimization perspective, but this type of geometric thinking is very important when we discuss classification, when we discuss the SVMs and maximum margin classifiers and clustering, nearest neighbors, as you have seen. It's all about half spaces, Voronoi diagrams. K-means clustering will be all about this. So some of the most popular things require some background knowledge like this. So it's better that we do it now. All right. Where are we then? And then this is actually not terribly important, the ellipsoid algorithm. So this is a fancier way of doing volume reduction, right? Ellipsoid has this formula in the n-dimensional space. So this is kind of a ellipsoid, volumetric one. And so this is in terms of x, such that there is the C, and then there is this matrix, positive semi-definite matrix, and inequality to 1. So this is how you define the ellipsoid shape in n dimensions. And the idea is very elegant. And then there is actually a nice Wikipedia page as well. And then it's not terribly, as I say, important, but shows you that you can do better than just putting half planes. So what it says is, let's start with the query the point at the center of the current ellipsoid. So what you do is you start, let's say, with a circle like this, ellipsoid like this, which is almost like a sphere-like thing. And then the center of it is this x0. And then you do a cutting plane. So the gradient tells you which part of that sphere to discard and which part of the sphere the solution is there, because the gradient tells you climb up or climb down, and if you are minimizing, there's no point in climbing down. You need to climbing up. If you are minimizing, there's no point in climbing up. Therefore, you need to climb down. You need to go to the opposite direction of the gradient, and because this is convex optimization, you cut off all that climb and try to reach the valley. So now you know that this is inside this half. Let me use my laser pointer. So now we know that this is inside here. So I haven't used the box. I've used the spherical-like shape as an initial shape, and then I discarded half of that shape. So the idea is now, elegant idea is, find the cutting plane divides into 2. Yes, we have done that. We used the gradient at that x0 point to do that, and then that gave us a half plane cutting. And then find the smallest ellipsoid that covers the half of the previous ellipsoid. So now I find this red one, which covers all that half shape, right? Now the all half shape is inside this red one. And then I go to this. So in that one, I find the centroid of that, x1. And then from that centroid, I find the gradient. And gradient, again, gives me a cutting plane. And from the cutting plane, I discard this side. I kept this side. And in this side that I have kept, you see, this is the thing I am tracing. I put a minimum ellipsoid covering that. Now you will say, how do I do that? There is a nice way of finding that ellipsoid. Okay? So the formula is actually not terribly important. There is a nice geometric formula. So now I do the same again and again. So I get smaller and smaller ellipsoids. then the solution will be inside the last ellipsoid. Then you make some epsilon error, of course. So that's another way of doing it. Just to give you an idea, it's not about necessarily boxes that you are cutting into pieces, and you can do it also with different shapes. The search. The cutting plane methods also are very popularly used in integer programming and discrete optimization, because there you don't have much of a gradient issue, so you need to use you need to divide the space into pieces. And as I said, the soft value of this whole stuff is as n goes to very large dimensional spaces, you will need a lot of, the shapes become very complex in those high dimensional spaces, curse of dimensionality. You need to then have many iterations, many constraints need to be tallied, and that becomes very cumbersome. So these are known as this is a finite dimensional or low dimensional methods for optimization. All right? Therefore, we will go to the very popular dimension-free optimization methods like the gradient descent methods, where you don't care about the dimension. You just take a step towards the right direction instead of dividing space into, chopping space into, search space into smaller and smaller pieces. Questions? Right? Any part that you are not comfortable with? Those of you who realize I need to look at my linear algebra, that's a good thing. You should. But other than that, conceptually, does it make sense to you? All right, good to hear. So now we come to the very famous gradient descent methods. There has been a huge renewal of interest on gradient descent because now it's used in machine and deep learning. There are a lot of interesting articles, popular articles on these blog posts and so on. The idea is very simple. The other one was going back to the number guessing game. The idea with the iterative descent is this. So let's assume a convex objective function that is differentiable, and we want to minimize. And these are the level sets, right? And then it's a valley. It's a ball chopped in the third dimension, and it's like a map. It would be then the sea. It would be then the ball-shaped, equidistant lines of the depth of the sea on the map will look like this. Then the middle ones will be darker blue, and then the closer to the shelf ones will be lighter blue, if you look at any band. So what do? We just start at a point x0 again, and we don't care about a search box or anything. We just iteratively jump, hopefully closer to the solution. Right? It's an iterative method. So we jump at each step from x0 to x1, x1 to x2, x2 to x3, and then, of course, we need the f function we are trying to minimize, so we want the x function to decrease as we jump. What's the point of jumping the other direction? We need to go towards the bottom of the ball valley. Well, of course, this is the whole idea. And then if I do it, many times, hopefully I'll come close. Right? I've said something, but I haven't said anything yet, if you have noticed. So I haven't said anything about how do I jump and what direction do I jump and so on. Now we'll come to those. So the question is, how do we choose the jump from xn to xn plus 1? So from 0 to 1, 1 to 2, 1, 2 to 3, right? And as you can guess, there are multiple ways of doing it. All right, let's look at it. First, also there is the issue of how much do I jump? Even if I know the direction, how big a step am I going to take is there, right? And another analogy that I really like is climbing up the mountain. So there's a mountain I want to climb, and the mountain is nicely convex shaped, inverse ball shaped. And then which direction am I going to climb, and how far is each of my steps? That will be the maximization version. So let's first focus on choosing the direction, because if I turn my nose into the wrong direction, no matter what step I take, I'm in trouble. And then let's pick a small enough step size alpha for now. So then we have this situation, xn plus 1. The next point is xn. These are all vectors, right, in a high dimensional space, minus alpha dn. Or alpha can, yeah, the plus minus sign, don't worry about it for now. That depends on whether you're maximizing or minimizing. Alpha is a small step size, but what is dn? That's the direction, right? Why should it be small enough? Let's say dn is the right direction, but I choose a big alpha. This is what happens. So I'm actually here, and then suddenly I take a big jump, you know, and then I go to the other side, and then jump back and forth. That's not desirable. If I take small step size, I can go down in a nicer way. So for now, the intuition is choose your step size small enough that you don't cross the solution, right? We will also discuss the step size in detail. So the idea is, how do I find D? Actually, we know mathematics, and then we don't have to go to high school level. We can actually use our math knowledge to kind of discuss what's going on. So we can actually do a Taylor series expansion at xn plus 1. So that would be then fxn plus 1. If I do a Taylor series expansion of the first order, it will be the xn plus the first order term, that's the gradient derivative, right, times xn plus 1 minus xn, right? So that's the direction. So first order approximation. Or I can do a second order approximation. That will be then the first derivative, second derivative. This is Taylor series expansion in multivariate, nothing else. So you have then the next one is I can approximate by the current one with the first order term plus 1/2 and the second order term, and HOT is the higher order terms. You know, of course, you can do an infinite Taylor series expansion. The whole trick is having access to the gradient and the second gradient here. You need to be able to compute it at your point, right? You're with me, right? Okay, so because this is the whole idea. So actually, if the objective function f is convex, you reach the minimum. Objective function f is convex. You reach the minimum bottom of the curve or landscape as long as you roughly point in the right direction. So the dn needs to be in the right direction, which means because of this minus sign in front of here, right? dn and the gradient should be, dot product of them should be positive. Right? That means that I'm going to the minus dn direction. Let me draw this immediately, because then there is no need to torture ourselves with drawing on the air. So the idea is this. So I'm at here. Let's say here, right? The bottom of the ball is here. So let's draw the lines like in a. So the gradient then will be. Let me use something else. So the gradient is very important. So that will be the gradient of f, right? So this is xn, f of xn, right? It will be climbing up because that's a ball. And then if the d is, you know, dot product of d and the gradient is positive, what does it tell you? Theta is, you know, less than, you know, cosine? That's the cosine and sine, right? Right, so if theta is, yeah, if theta is plus 90 and minus 90, the cosine theta will be positive, right? So that means as long as d is directing, you know, this direction, then d dot fxn will be positive. And if I remember, there was a minus sign in front of the dn alpha. Alpha is positive. So therefore, xn plus 1 equals xn. Then you have minus alpha. So you have plus alpha. And then you have minus d. So that means I'm going this way. I'm going alpha times minus d. And that will be my xn plus 1. See? Then minus d will be then dot product of minus d with the gradient will be negative. You need to be just careful with the sign because you may be maximizing. Then you need to go up, right? Then you need to have a plus. So it's usually easy to do when you code it. If you do a minus sign, just switch to the minus. Then you go. You should not climb instead of going down when you are minimizing. Yeah? Is this clear? Again, the geometry of it, the vectors. When did you see the vectors last time? These vector dot products and. Has it been decades? I mean, wasn't there a math subject somewhere that has some geometry in it? And I hope so. If not, let me know. Right, so this is the whole idea. So I'm kind of, so in layman's terms, again using the mountain analogy, if I'm trying to climb the mountain, as long as my nose is kind of towards the direction, as long as I'm climbing, right? If I stay at the side of the mountain, the gradient is the slope, right? So as long as I'm climbing, that means I'm climbing. That means it's a good direction. Maybe if I'm very badly climbing, I'm going to do this, it will take a long while to go up, like the cars do, because you cannot have a tight slope. But as long as I'm not descending, it's okay. So the direction is as that. And then that means my nose and the gradient, in the climbing case, should have a degree that is less than, within plus minus 90 degrees, because otherwise I'm descending. Right? It's very intuitive, right? And that's the whole idea. Once you get this, there's no more to it. Okay. Steepest descent. So, but I don't want to just get it right a little bit. I want to go the steepest descent when I'm minimizing, or steepest ascent when I'm maximizing. Then what would I do? I'm greedy. I want to climb as fast as possible. Then I need to just follow the gradient, because that's my local information at that point. So you can choose D to be gradient of F. Then the dot product will be the, the norm square, which is greater than 0. And actually, that's the best you can do in terms of direction. Right? So that would be then the steepest descent. Right? The basic principle is this. But then I should have, sorry. You see it, right? Yeah, very good. Yeah. To tell me if you don't see what you're supposed to see. I sometimes. Okay, and then I guess the famous Newton method. So we can actually use the basic principle stays, but actually we can use the gradient is a first order approximation, the tangent at where you are. Why don't we use the quadratic approximation? We can, right? So in that case, then the point x, I'm at xn, and the next point fa at any x, the value of the objective function at x, can be written as a Taylor series expansion with respect to xn, like we did. Right, so yep, that can be written like this. And then we take the derivative of this parabola. We create this multi-dimensional parabola. In the one-dimensional case, it is simply fx plus derivative of fx, and then this is the second derivative of fx and the square. Right. So it's just if you find this confusing, write it in one dimension first to give the intuition. I wrote it in the general case because it's easier to go back to the one dimension from multi than the other way around. So if we take the derivative of the parabola and set it to 0 to find its minimum, so we can actually take its derivative, and with respect to x, so this, then what do we have here? We have this, and then we have got this coming in. We have this derivative equation. And then now we use this to decide on the direction. So if we use this as the direction. So we have then f of xn, xn minus xn. So the second derivative here inversed, right? Then we multiply with inverse. Then this cancels out that. We have the inverse here with this one. And then that here brings x minus xn, right? Then if we take everything to this hand side, then we have xn minus the inverse and this multiplied, and then we put an alpha in front of it to step size, to you know, adjust our step size. So we got this. We got this equation, and I need to stop. So I'll derive this a bit more next time. But I want to show this figure. So here, you don't have the gradient. Now you use also the second derivative and Hessian of the matrix. So in the steepest descent, this is really nice. So at any point, you use the gradients to go down. You use the gradient direction, first order. What you are doing in the Newton method, at any point, you are not looking at the tangent, but you fit a parabola to where you are, and you go to the minimum of that parabola. This is a really explanatory figure. So you do a second order approximation. So I'm here, I do a second order approximation to my function and go to the minimum of it. Then I'm here, I do a second order approximation to local approximation to my function and go to the minimum of it, and so on. The second order approximation is more sophisticated, but you need to work harder for it. You need to take the second derivative, or you need to find the Hessian in the multivariate case. The first order, finding the gradient and finding the tangent is much easier, right? So that's the trade-off. But then this may put you closer to the optimal point much faster with the Newton method, as long as your approximation works well. So I will come to this and then do the questions, continue next week. And I will post the constraint optimization slides today, and we'll continue with constraint optimization after we are done with non-constraint. So see you next week.